Hello everyone, and welcome back to this Nanophotonics and Plasmonics course. Now we do have introduced the principle of Raman scattering and discuss how plasmons can enhance the Raman scattering effect. Now it's important to dive into what type of substrate and plasmonic structures can be used for TERS. So there's been over the years a wide range of substrates that have been developed, going from randomly oriented nanoparticles, very dense nanorod arrays, ensembles or more organized pillars, to three-dimensional substrate where you have nanoparticles that are really embedded into the fibers of paper or fabric. And even more sophisticated and highly organized nanoparticle arrays. The whole board game of the design of substrate is to achieve a very large density of plasmonic electromagnetic hotspots where you have highly localized electromagnetic fields. So you can redesign the type of substrate you want, and you can also design the type of nanoparticle you want. So you can really do TERS from plasmonic nanoparticles. This is just examples comparing spherical gold nanoparticles, which are ideally spherical and smooth, to particles that are highly porous. So those particles with similar sizes now exhibit a lot of pores on the surface, and as a result of the pores, you have now very strong localization of the electromagnetic field at the surface of the nanoparticle, as opposed to this clear dipolar resonance. If you excite the particles with the different sizes at the plasmon resonance wavelength for each of these cases, you can integrate over the volume how much field you have, how much field enhancement you have, and elevate that to the power 4, and you can get basically an estimation about TERS enhancement factor, which is just the fourth power of the local electric field enhancement, as we discussed in the previous video. From this graph for the different nanoparticle sizes, it becomes obvious that the porous nanoparticles in orange here provide a much stronger surface enhanced Raman spectroscopy enhancement as opposed to their smooth counterparts. And you see that you have a factor of 10 to a factor of 100 times more enhancement with the presence of pores at the surface for comparable sizes. And this can be actually observed experimentally. So experimentally, you can perform TERS experiments with different nanoparticles, different sizes, or different type of morphologies, and you realize that if they're highly porous, they provide very strong enhancement of the Raman signal, as opposed to very smooth nanoparticles like we have here in black. So the stronger the field, the larger the enhancement factor, the more intense the TERS signal. So you can really design this different type of substrate, of morphologies, and this is another example of substrate which is commonly used in TERS, which is called a film over nanoparticle, a foam. And those foams basically are just based on silicon beads. So you have silicon microspheres, and then that are packed together, and then basically you deposit metals on top. So it could be silver, it could be gold. And the result of this deposition gives you these very rough surface on top of these silicon beads, and that provides a lot of electromagnetic hotspots where the electromagnetic field resulting from the plasmon excitation is very strong. So this is just a cross section of such a nanostructure, and you see that you have strong electromagnetic fields in the vicinity of these grooves in between the spheres. And if you look at how the TERS signal evolves when you move away from the surface of the metal, you see that the TERS signal drastically decreases as you move away from the nanoparticle surface. So you have this exponential decaying enhancement factor or TERS signal as you move away from the surface. So you can distinguish actually a short range and long range dependence of the TERS signal on the distance. So something that have been of interest for applications is single particle TERS. So single particle TERS can be extremely beneficial because you can really very compact devices, sensing platforms. Especially if you design one single dimer of nanoparticles, you can really design and engineer these dimers so that the gap in the middle is very small, and then basically you achieve extremely large plasmonic hotspots in this gap. So this is the case for a dimer. You can also have pointy or tipped nanoparticles that exhibit also very sharp features that are gonna localize very highly localized fields. So in a dimer like this, basically you can achieve 10 to the 8th for the enhancement factor. That's something we discussed in the previous video, and it's basically achieved in this kind of dimers that have been synthesized in a group of Rick Van Dyne at Northwestern University. So they are basically the world record for enhancement factors. So those large signals coming from a small amount of analyte is achievable in this kind of configuration, and typically people can achieve picomolar or even attomolar concentrations. So you can also, as I said, use particles with sharp features. So these are like very highly porous and with particles with spikes and everything, and you can achieve very low concentrations of 10 to the negative 11 molars. So it's because of the presence of all those pointy features and sharp features on the surface of the nanoparticles. The porosity very similar to the porous nanoparticles I've shown before. So this can be achieved on single particle level. Something which is a little bit more challenging, but which is also kind of a holy grail of TERS, is to perform single molecule TERS. So the idea would be to be able to do TERS measurement on a single molecule. So the existence of single molecule TERS has been already proven, and basically by just employing isotopes of the same molecule. So in that case, it's rhodamine 6G, and because you just replace the hydrogen atoms on one of these ring by deuterium atoms, you change the mass. Because you change the mass, you're gonna change the frequency of those vibrations, and because you change the frequency of those vibrations, basically you're gonna have spectral shift of some of these resonances. So most of the resonance will appear at the same frequency, but you're gonna have some distinct peaks that are gonna basically distinguish between the two isotopes. So if you use a combination, a mixture of those both molecules, and then you know that for one of them you're gonna have those peaks, for the other one you're gonna have this peak, then if you measure the signal coming from a particular location on the substrate, and you measure one spectrum or the other, you know that you have a single nanoparticle. If you observe a mixture of both spectra, then you know that you have at least two molecules. So this is the way they proved that statistically an average of one molecule absorbed on the nanoparticle basically give you only one of these two spectra. So this can be done also on the dimer, at the dimer level, so that they have done this on this kind of configuration where you have this dimer and you have those molecules that are in the gap here. So single nanoparticle TERS, single molecule TERS, and something which is also related to TERS is basically the tip enhanced Raman spectroscopy or TERS. So what is TERS? Well, basically it's just very analog to TERS, but instead of performing the Raman spectroscopy enhancement with any random plasmonic structure, we basically use a tip. So it's typically a metallic tip, which is brought into close proximity to a substrate. So typically they are metallic substrate, but it could be also dielectric. And then basically you have the molecules that are laying down on the substrate, and you just bring the metallic tip close to the molecules so that the molecules basically sits in the gap between the tip and the substrate. And the plasmonic hotspot, or the region where the local electric field will be enhanced, will be actually in the gap between the metallic tip and the metallic substrate. So very similarly to TERS, there's also single molecule TERS that have been achieved. So using the same mixture of rhodamine 6G isotopes on the substrate, and people are able to measure either one or the other, or a mixture of both. So you have a single molecule of this blue version of the rhodamine 6G, or a single molecule of this red version of the rhodamine 6G, or a mixture of both here. So you have at least 2 molecules, if not more. So these are both very powerful techniques, TERS and TERS. Now we're gonna basically move to something which is exploring a different aspect of the localized phase plasmon resonances, and that's basically the localized phase plasmon resonance sensing. So LSPR sensing is a different type of optical spectroscopy. You're basically looking at the absorption or scattering spectra, and you're looking at how this optical spectra changes as you change the surrounding medium. So when you change the surrounding medium, the direct permittivity of the surrounding medium, you're changing the plasmon resonance. We've discussed that extensively in chapter 9. So you can also design the nanoparticles with different morphologies or different compositions to really optimize the sensitivity you have with respect to the change in refractive index. So these are just a few examples of a cube, a concave cube, a nanorod, and a prism. And you see, for instance, that the cube experiences a shift of the plasmon resonance of about 7 nanometers when you change from water to a refractive index of 142. On the other end, when you have something with high aspect ratio like the nanorod or the prism, for the same change of refractive index, you can achieve a spectral shift of the LSPR of up to 35 nanometers. So those two, for instance, are more sensitive to a change in a refractive index. So there's been a lot of work done over the years designing better and better plasmonic sensors. This is just a table illustrating some of these different nanoparticles that have been combined by Katie Mayer when she was doing her doctoral work in a group of Jason Hafner at Rice University. They wrote this review paper, basically where they went through an extensive literature survey about the different nanoparticles that have been synthesized for LSPR sensing, the type of ensembles or single particle, and then basically giving some properties like the localized plasmon resonance, wavelength, and how much this plasmon resonance can shift when you change the refractive index. So this is the amount of shift per refractive index unit. So this is just to give you an idea about the different morphologies and how good those different morphologies perform as LSPR sensing platforms. So now these are sensing applications for bulk refractive index. So this is the bulk LSPR sensing. So you're changing the overall dielectric environment. You're changing the overall refractive index. Now you can also go towards single molecule detection and try to detect a single molecule arriving onto the nanoparticle or in the vicinity of the nanoparticle, or a single particle leaving the nanoparticle. So this molecular LSPR sensing has also been performed and been shown. So you can use both SPPs. So if you use a metallic film, you excite this in a total internal reflection, you generate those evanescent modes, those SPPs at the surface, and then you have this flow channel where you have those molecules that can be functionalized at the surface of the gold, and then basically you can try to detect binding and unbinding events of those molecules in the vicinity of the gold surface. So this has been also done by Katie Mayer and Jason Hafner on single nanoparticles using gold nanoprisms. So those gold bipyramids and nanoprisms basically are functionalized to be able to capture antibodies. And then when you have those antibodies that basically are captured by the nanoparticle, try to detect those events. So that they performed scattering measurements using this dark field scattering measurement configuration, measuring the localized phase plasmon resonance of those bipyramids. So you see that you have a nice dipole resonance, and then basically that they tracked the position of this peak as the flow of these antibodies occurred. So what they have measured is basically just very tiny shift of the plasma resonance to see that the peak shift is sub-nanometers. So you have very sub-nanometer nanoparticle, but you see those distinct steps here and here, and those steps are basically binding and unbinding events of single molecules on those gold bipyramids. So this is totally possible to detect single molecules using plasmonic nanoparticles as biosensors. There's been a lot of work also done using nanoparticles as sensors for more practical applications that you can find anywhere, like pregnancy tests. So this is just an example of a lateral flow assay basically that can be used for pregnancy test. The idea is basically to use the gold nanoparticles, typically 40 nanometers in size. That's popular because they exhibit a plasma resonance about 423 nanometers, which is very red, cherry red, so it's very distinct color. You can very visualize this, and the idea is basically you have those nanoparticles that are sitting on this strip. You place the urine sample here, and then you're gonna have some eventually binding events of the hormones you want to detect on the nanoparticles. Those nanoparticles will flow and basically will be stabilized on those lines. So there's the control and the test lines, and then as they start immobilizing there as a result of the presence of these hormones on top of the nanoparticle surface, then basically you're going to start seeing the red appearing. So this red appears as a result of the interaction of the visible light with those nanoparticles. And this is the spectra of those nanoparticles with the plasma resonance around 520 nanometers in size. This is some examples of those colloidal nanoparticles. So the shade of red is really given by the size of the nanoparticles, so where the spectrum is going to sit, and the intensity of the line here will be directly connected to the amount of hormones that will be bound to the nanoparticles at the test and the control lines. So this is something which is extremely powerful. Another example of plasmonic nanoparticles used as a sensor. So to summarize this chapter, so we've discussed about the different optical processes forming like matter interaction, talking about emission and absorption processes, elastic and inelastic light scattering, and then we focus on Raman scattering, especially the case of enhanced Raman spectroscopy. So we introduced the concept of TERS, and then we discussed the enhancement mechanisms, which is basically governed by the presence of the localized plasmon resonances, which then introduced the enhancement factor, which is proportional to the fourth power of the electric field. So this is very important to remember. And then we discussed about single particle and single molecule source and TERS before finishing up on LSPR sensing for both refractive index sensing and molecular sensing.